Swayam Prabha. Digital India. Educated India.
Now, this is a blown out picture of all the components that you see here. So, first is, please understand, there is no camshaft, there is no timing gear, there is no tappet, there is no valve, there is no valve seat. So, the number of components that are required to make this engine will be much less, which makes it mechanically much less complicated compared to a reciprocating engine. Okay. So, let us look at how this looks like. So, this what we are looking at is, this is a 2 rotor engine, 2 rotor Wankel engine. So, these are the 2 rotors, okay, and you can see both of these rotors have internal gearing built in them. So, they go inside this housing and this housing. This is the central part, okay. So, this is the rear housing, number 1, this is the rear housing, okay, and this is front housing. So, these are the outer housings, and then this is one rotor housing, this is another rotor housing, 2 rotor housings, and this is the intermediate housing. Okay. So, here, here and here, in these 3 parts you will have bearings, okay, and this rotor will go inside here, this rotor will go inside here, and these are the fixed gears. Number 8 is the stationary gears. So, these gears will be not moving, they will be fixed, okay, and you can see this shaft here, okay. So, this rotor will be here and here, 2 rotors will be located here. So, when the shaft rotates, these rotors will be moving up and down, right, and here you have number 7, which is the electronic throttle. Throttle is basically to control the supply of the fuel air mixture. What you have number 5 is the intake manifold, resinous intake manifold, so it is made of plastic, okay. This number 6 is the intake manifold. So, this resinous intake manifold goes on top of it, and then this is mounted on the engine, and this is the exhaust manifold 11, this is the exhaust manifold. So, this is how the components look like for a 2 rotor Wankel engine. So, this housing is roughly oval in shape, not exactly oval, because oval, this is one type of circle and then this is another type of circle. So, this dimension is actually less than the diameter of this circle, okay. So, this geometry is actually called epitrochoid, okay. The shape of the combustion chamber is so designed that the 3 tips of the rotor always stay in contact with the balls of the combustion chamber. So, here if you see, the rings are here, and below these rings there is a spring. So, the spring function is to push this ring, so that you always maintain a positive contact with the liner, and the idea is that you should not allow the gases from this chamber to pass to this chamber or this chamber to this chamber, basically to insulate them from each other as far as possible with practical limitation. Absolutely sealing them, is it possible? It is not possible. Some charge will go from here to there or there to here. I will tell you, this affects the emissions, but you try to seal it as far as possible. So, again, just like any other reciprocating engine, there will be 4 parts of a cycle: intake, after that intake we will have compression, after the compression you will have combustion and then expansion, and then you will have exhaust. So, here also you will have all 4 activities taking place. The intake and exhaust ports are actually located on the housing. So, one port is here, the other port is here, and here you have the spark plug. There are no valves, okay, and the exhaust ports connected directly to the exhaust, and intake port connect directly to the throttle, and then through the throttle it is connected to the intake manifold, okay, or intake manifold and then throttle, depending on what configuration you want. Please notice here one thing, that there is no fin here. These are the ports here, intake and exhaust port. There is no fin here, but there are too many fins here. Why? Because this is the intake, so this will be the cold region. The cold fuel air mixture is coming in. You don't need to dissipate too much of heat. Heat starts building up when you compress in this region, and it peaks here when you have the combustion, and then here you have the expansion. So again the temperature is going down, and at the exhaust again the temperatures will be relatively quite low compared to combustion stage. Okay. Now question is it enough to seal on only these two phases? So the answer is no, it is not possible, because they have to be sealed from the sidewise as well. Okay. So rotor has 3 convex faces, each of which act like a piston. So each side is acting like one piston. Okay. Each face of the rotor has a pocket in which which increases the displacement of the engine. So you can see here that there is some pocket, some groove. If you look at this engine, for example, if you look at the pocket here, there is a pocket here. You can see that white patch here. Okay. So that's where you basically control the compression ratio, and you allow more volume of fuel air mixture to come in. Okay. At the apex of each face here, you have seals, because you don't want the air from here to come by here and go to this side. So you provide sealing here, and you provide sealing here. So all these areas are sealed totally on both sides of the rotor. Okay. At the apex of each face is a metal blade which forms the seal to the outside of the combustion chamber. There are metal rings on each side of the rotor that seal the side of the combustion chamber, and it is the gear meeting that decides the path and direction of that the rotor takes through the housing. Okay. So this is quite important, you see here. So this is eccentric shaft. If you look at, this is the center line. So this bearing, one bearing here goes to the left side housing, this bearing here goes to the right side housing, and this bearing here goes into the central housing or intermediate housing, and this is where you will have first rotor, this is where you will have second rotor. So you can see the design itself, this acts as a crankshaft. This does the same function as crankshaft in a reciprocating engine. Okay. So the output shaft has round lobes mounted eccentrically. These are the that is, they are offset from the center line of the shaft, and this is cylindrical, because the rotor, if you look at the rotor, this image here, you can see this is also cylindrical. So this shaft, this one has to be perfectly cylindrical, but the center will be off center from the axis of the shaft. Okay. So each rotor fits on one of these lobes, one goes here, one goes here, and then you could also have other design which could have 3 rotor engine or 4 rotor engine. So depending on how many rotors you have, you will have such lobes. Okay. The lobe acts as a sort of a crankshaft as in a piston engine. As the rotor follows the path, follows its path around the housing, it pushes on the lobes. Since the lobes are mounted eccentric to the output shaft, they force the force that the rotor applies to the lobes create torque in the shaft, causing it to spin. So you see here, if there is a pressure generated, so this pressure will push this rotor, and this rotor in the center you have the shaft. So finally this gas pressure through this eccentric shaft will get converted to rotary motion. It will force the shaft to rotate. So that's how the gas pressure is converted into rotary motion. Okay. Now I can tell you very interesting things. There is a internal gear, and then there is a stationary gear. It's a very intricate geometry. This is the triangular rotor, and this is the fixed gear which is external gear, and then you have this internal gear which is a part of the rotor. Okay. And you see this is the shaft, central shaft, So, obviously, this is the center of the entire shaft, one center line, and this is the center of the internal gear, and there will be some eccentricity in between. Okay. So, this is the rotor gear, this is the stationary gear, and this is the arm. So, the phase gear consists of the inner tooth gear ring fixed on the inside of the rotor and an outer toothed gear fixed to the eccentric shaft. The rotor of the, if the rotor gear were to have 30, suppose this is the 30 teeth gear and this is 20 teeth gear, then the gear ratio will be 3:1. Okay. In this also you have the same configuration, 30 teeth outside, 20 teeth for the external gear, 30 teeth for the internal gear. So, due to this gearing ratio, rate of turning speed between the rotor and the crankshaft is defined as 1.3. Now, this is very interesting, please note this. You know, this is a triangular rotor, this is a spark plug here, and these are the two intake and exhaust ports. Okay. I want you to focus. So, suppose right now at this stage, this is the shaft, this wheel in the back is connected with the shaft. So, if I rotate it 4 times or 3 times, the shaft will rotate 3 or 4 times. This is basically shaft only. Okay. So, now please see here this face, okay, just focus on this one edge, and this has 30 internal gears tooths and fixed gear has 20 external tooths. Now, I am going to rotate this, and please see when this particular ring comes back to the same position, how many times I have to rotate this. So, please focus on one, you can focus on this one or any one of these. Okay. So, I am not rotating now. So, please see this is 1, so it has come here from there, this is 2, this has come here, and this is 3, it has come back to that same place. So, 3 times shaft rotation and 1 time piston rotation, that is what is achieved by the triangular piston. So, what I am trying to say is that when the piston rotates 1 time, the shaft rotates 3 times. Okay. So, suppose you want a engine which is rotating at say 3000 rpm. So, that means the triangular rotor will be rotating at 1000 rpm because of this. Okay. So, due to this gear ratio, the rate of turning speed between the rotor and the shaft is defined as 1:3. The rotor has longer rotation period than the eccentric shaft. Eccentric shaft will be rotating much faster. The rotor rotates 1 turn while the eccentric shaft rotates 3 turns. With this, the engine running at 3000 rpm, the rotor will rotate at merely 1000 rpm. Okay. So, I think then there is a little bit of explanation of geometry. Stationary part of the Wankel RC engine has inner contours of 2-lobed epitrochoid, in which rotor rotates a rotor having an equilateral curve sided triangular shape, and then there is a little bit of a mathematical explanation of what is the epitrochoid and how we make it. I do not want to go into those details. Okay, this is also showing that why you have this epitrochoid kind of a circuit, okay, design. So, here you see the major diameter of this epitrochoid, that means from here to here is r plus e and the minor is r minus e. Okay. Okay, so, if we look at the working of the Wankel engine, to understand it, let us focus on one of the edges of the Wankel engine. So, this is the intake port, let us focus on this edge. Okay, so, when this edge is this rotor is rotating, this volume will be expanding, and since this volume will be expanding, air will be sucked in, air fuel mixture will be sucked in. Okay, so, this will be filled with fresh charge. This charge moves, and when it comes to this side, the volume actually reduces. So, as a result, this volume of fuel air mixture will now be contained in a very small amount of volume, small volume, and this will be high pressure, high temperature mixture. And then you apply a spark just like you do in a normal spark ignition engine. As a result, the combustion will take place, and then this will expand, and the gas force, since it is moving in this direction, momentum is also in this direction. So, gases will push this piston in this direction, and it is connected to the connected to the shaft. So, this shaft, this rotor will rotate and the shaft will also rotate in terms, okay, and then it moves up to here. So, up to here, when this edge is here, up to that time it is expansion stroke. The moment it uncovers the port, exhaust, because of being in high pressure and high temperature, will start going out, and the exhaust will go out, and then this edge will move further up to here. Whatever is the exhaust here, contained exhaust here, that will also be going out, okay. And this is how one cycle for one particular edge will be completed, okay. And obviously you can see here there are 3 edges. So, all the 3 will be doing different things at different times. So, one shaft, one rotor rotation will essentially mean that there will be 3 power strokes, or 3 times the expansion of the gas, okay. So, the heart of the Wankel engine is obviously a 3-sided piston, which is called the rotor, which involves the housing, which revolves inside the rotor housing. As the rotor moves, the volume starts to shrink, compressing the intake fuel air mixture. This mixture then passes over the spark plug set into the valve for the housing. The spark plug then fires to ignite the mixture, causing it to expand and drive the rotor. I will explain this to you by this model, okay. So, right now this is the intake port and this is the exhaust port. The top port is exhaust port, this is the intake port, okay. So, suppose you just focus on this, okay. So, now the exhaust, this is the exhaust is going out, and then now moving here. So, the fresh charge starts coming in. Look at this volume, the volume is small now and it is increasing. So, when it is increasing, the vacuum is being created. As a result, it will suck in the fuel air mixture and then the volume increases. So, now this is filled and exhaust intake port is still open, okay. The moment I go forward, intake port is closed, the entire volume, so much of volume is filled with fuel air mixture, okay. And then I rotate it further, and so you can see that the volume is now shrinking, okay. So, if you look at it here, the volume now is very, very low. The compression is, high degree of compression has been achieved, and then it comes in front of the spark plug. Just like I apply the spark, fuel air mixture will burn, gases will be pushed. So, then high pressure, high temperature gases will start pushing the rotor in this direction, and it will expand. See here, focus on this edge. You are expanding up to here, okay. So, up to here it is the expansion stroke. The moment it goes further down, it uncovers the exhaust port. Because of the higher pressure, the gases will get flushed out because of the pressure difference. And then whatever gases are remaining, now when it is fully uncovered, there will be atmospheric pressure here, but the gases will still be there. So, those are pushed by reducing the volume. It is similar to the process of exhaust stroke in a reciprocating engine, okay. And then basically all the exhaust gases are pulled out and the intake stroke coming in, okay. So, this is how this one cycle works for a rotary engine, okay. So, I hope the working is absolutely clear to you. At this point, the volume between the rotor and the housing increases to allow the expansion of the gases. Finally, the volume decreases, and you have seen that there are all 4 strokes, and there are 3 power strokes for each revolution of the rotor, okay. So, as the rotor rotates, it drives the shaft carries the rotary motion to the transmission, and then finally it is delivered to the wheels via some appropriate gearing mechanisms and shafts, etc. Okay, and here all this explanation of 4 strokes. So, you can see this is the pocket in the rotor which increases the volume, okay. So, when it rotates, this whole thing is filled with the air. So, that means it is induction. When it is closed, it undergoes compression, fuel air mixture is compressed, and then you see it comes here, and then you have 1 spark plug or 2 spark plug, you can have any design. You apply the spark, combustion happens, pressure temperature rises, and then you have power stroke, and finally you have the exhaust, okay. So, these are the 4 strokes that happen. It is very similar to a reciprocating engine, all the 4 processes that take place. So, if you look at the important features of the rotary Wankel engine, there is absolutely no reciprocating part, okay. So, therefore, you do not have to balance any force. One of the big problem with reciprocating engine is balancing of primary and secondary forces, and that gives rise to noise and vibrations. Okay. So, here the vibrations will be very less, noise of course combustion is taking place, so combustion noise will remain there, but the noise because of the reciprocating parts will also be very, very low here. Okay. So, this is one big plus here, that there is no problem of unbalancing, and then vibrations will be low because it is possible to perfectly balance the engine using the balance weights. Okay. So, there is no problem in as far as balancing is concerned. No separate intake exhaust valve mechanism. So, there is absolutely no valves, okay. It is all ports, there is nothing which moves, okay. There is no crankshaft, okay. There is no camshaft, and there is no tappet. Okay. So, completely all the valve mechanism, opening and closing, all this is completely eliminated, and even at high speeds, ports works perfectly fine, whereas valves do not. Okay. Now, lubrication in rotary engine can be quite challenging. So, if you look at the lubrication system, it is divided in two parts. First is you have all the rotor housing, phasing gear, shafts, etc., that needs to be lubricated, and second is whatever is inside the combustion chamber, that needs to be lubricated. So, lubrication of the apex seal means the one which is on the top or on the bottom, side seals and the bore, all this also needs to be required to be lubricated. So, the first part, two separate circuits are formed from one oil sump. So, there is only one single oil sump, but two separate circuits, one to lubricate the rotor housing, phasing gear and shaft, the other one for apex seal, side seals and bores. So, if you look at the circuit 1 for rotor housing, phasing gear and camshaft, the circuit is like this. There is oil sump, then there is a small oil pump, then there is a filter because you do not want any debris to go into the lubrication circuit, and then there is oil cooler which will reduce the temperature of the oil. There is a main oil line, and then from that main oil line you have galleries which will take the oil to the main bearings, eccentric bearings, rotors and side plates, and then whatever is the excess oil, it will come back to the oil sump. So, this is one circuit, and the second circuit is where the oil in the sump is fed to a dosage pump. So, you have a small dosage pump of a small variable stroke type metering pump. So, very small volume it pushes. The dosage pump pumps the oil into the fuel pump. So, you are basically mixing the fuel with the lubricating oil, just like we do in two stroke engine. You remember two stroke engine, earlier scooters you used to add 2T oil, 4-stroke engines do not require. Why you used to use 2T oil? Because there the oil sump was dry. Okay. So, here what we do, we deliberately add 2T oil in the fuel in a measured quantity, or in the carbureted float chamber we introduce that oil. So, the fuel mixes with the air, and along with the fuel mixes with the lubricating oil and air. So, all this mixture of fuel, air, lubricating oil, that goes into the combustion chamber. Fuel will burn, but lubricating oil will lubricate all the seals. It will not burn because it is heavier molecule, right. So, after mixing with the fuel, this oil lubricates the seals, and then finally it also gets consumed because ultimately it is exposed to very high temperature, but it does the job. So, obviously this lubricating oil that you are putting will ultimately get converted to unburnt hydrocarbons. It creates a pollution problem, but it lubricates. So, you have an oil sump, there is a dosage pump which is connected to fuel pump, then fuel air mixture is formed, combustion is done, and then lubrication also happens in the process. Okay. So, this is the second circuit for lubricating the rotary engine. Let us look at the performance and compare it with the reciprocating engine. So, there are two engines, you see here, this is the engine speed in the RPM. So, 1000 RPM to 6000 RPM, and this is the BM, this is basically brake mean friction pressure. So, FMEP, frictional mean effective pressure in bar. Basically, it shows how much mean effective pressure is being lost to friction. Okay. So, this is the reciprocating engine which is 1800 cc. So, you can see 1800 cc engine maximum goes up to 5000 rpm and lot of friction is there. Now, this is the rotary engine which is 2 rotor of 500 cc into 2. So, 500 cc into 2 rotors. So, this obviously the swept volume is less and it has much lower friction. So, if you look at 5000 rpm, compare that with this, it will be at least 30% lower. So, frictional losses are much lower compared to the reciprocating engine. The other point that you can note here is that the power being produced by a 1800 cc engine is produced by 500 by 2 cc engine. Why? Because there are more number of power strokes per rotation of the rotor. Now, if we also compare the other performance parameters, say here is the speed, engine speed, and here is the shaft power output. So, this is the solid line is for rotary engine, which is 573 cc into 2, and the dotted line is for reciprocating engine. So, you can see this is the dotted line and this is the solid line, this is the shaft output. So, you can see that in the low speed range, the rotary engine actually produces slightly less power, but you have to also keep in mind that you know cc is also significantly lesser, but in high speed range this pretty much matches the reciprocating engine torque requirement, etc. Okay. If you look at the shaft power output, torque output, shaft torque. So, this is the rotary engine performance and this is the reciprocating engine performance. One thing that comes out very clearly is that at low speeds the torque produced by the rotary engine is not very high. Reciprocating engine give you higher torque, and because of which this power output is also low. Okay, but at high speeds this performance of the rotary engine is far better than reciprocating engine. The other one is mean effective pressure. So, mean effective pressure of the rotary engine is significantly less compared to reciprocating engine, but still you are getting, even at low MEP you are able to get almost comparable shaft power output. Okay. So, you do not really need to turbocharge it to that extent. Okay. So, the rotary engine has a slightly lower power output at low speeds, which is mainly due to greater time required for compression and combustion. So, 1.5 times longer than the reciprocating engine, which causes some gases to leak. Okay. So, at low speeds actually the seals are not very effective. So, chamber leakage from one chamber to another takes place at the edges, right. So, but there is higher output at higher speeds. This is attributed to smaller friction losses of the engine even at high speeds because of the absence of reciprocating mass, and a high charging due to longer intake and exhaust strokes. Intake and exhaust strokes are quite long here. Okay. So, you can actually, the volumetric efficiency is also better, that is why the power output is also better. And the absence of intake and exhaust valve, intake and exhaust valve, what they do, they apart from controlling, they also act as obstruction in the flow of intake and air. There is no valve here. So, the intake and exhaust gas can easily flow in and out of this engine, and that is why at higher speeds the outputs are also better. If you look at the fuel consumption performance and heat balance, here the excessive air ratio is shown, and here you have the distribution of the heat generated in the engine. So, you see here this is all experimental data of the heat balance, basically heat balance sheet of rotary engine. So, you can see here this is the effective heat, basically effective heat means the heat which is used for doing useful work, shaft power output. Okay. And this is the heat dissipation by lubricating oil. So, significant amount of heat is absorbed by lubricating oil, and then this is the cooling, heat absorbed by the cooling losses, and this is the exhaust, and these are other losses, and then these are basically unaccounted losses. So, this is the heat balance sheet of the rotary engine. Vibrations, if you look at the vibrations here, you see this is the 2 rotor rotary engine, 2 rotor Wankel engine is shown here, and here it is 4 cylinder reciprocating engine, this is 6 cylinder inline reciprocating engine. Okay. On the y axis you have torque, in Newton meter. So, torque values, this is shown here for all these three, and what you can clearly see, all these three engines are generating mean torque of 165 Newton meter. Okay. So, which engine will be vibrating the least from this figure? So, obviously, the most vibrating engine will be 4 cylinder. The moment you increase the number of cylinders, the balancing will be better, and therefore, in a 6 cylinder reciprocating engine, the unbalanced forces will be less. So, this will be vibrating less than 4 cylinder, but this 2 cylinder, if you make a 2 cylinder engine reciprocating engine, these will be far higher. So, 2 cylinder engines actually vibrate quite a lot. Single cylinder is the worst in terms of vibration. Okay, you must have sat in some of these Vikrams, they vibrate so heavily. Why? Because they use 2 cylinder engine. Okay. Cars do not vibrate that much, but if you sit in some, say, locomotive or some other device where there are more number of cylinders, the vibrations will be much less. Okay. So, rotary engine, you can see that rotary engine, the vibrations are far less. Okay. Then housing needs to be cooled. So, cooling, again we discussed engine cooling. The two types of coolings can take place. One is the air cooling, the other one could be liquid cooling. So, air cooling, you have to basically, wherever you, obviously when you have air cooling, you have to provide fins, and also you have to see which components are the most heated components. So, in this case, which area will be most heated? This area will be most heated where the spark plug is, because that will be experiencing highest temperature. So, what you do, you provide some kind of a hotspot accelerator. So, you increase the velocity of the air, so that cooling is better. Okay. And then there is a downstream, here also you experience a lot of temperature. So, you have some external construction. So, this is the story for the air cooling of the housing, and this is the story for water cooling. Now, this is 2 rotor system. So, one rotor will be here, other rotor will be here. This is just the flipped picture. So, this is the intermediate part, and this is the this is these are the end plates, and this is one single rotor housing. So, you have 2 ways to actually cool it by water. One is that you can have water circulation in this direction. Okay. So, this is called axial flow cooling system. So, the coolant actually flows in the axis of the shaft, that is called axial. Somebody may not like this configuration, and he says that I will like to do it radially. So, yes, you can do it radially. So, these are the plates, this is the housing, and you have the coolant coming in, and then the coolant goes in and out like this. Okay. So, this moves up and down. So, this is circumferential cooling. So, both mechanisms are possible with the rotary engine. So, these are just 3 different options that you have for the rotary engine. One is the air cooling system, the second is the axial cooling using liquids, and third one will be circumferential cooling, and all of them have their own advantages and disadvantages. Okay. Then you also need to cool the shaft, etc., because they also experience a lot of heat. So, this cooling normally is provided by the lubricating oil, and the lubricating oil has hollow shaft and hollow passages. So, oil comes in, and then there are galleries, and then it flows and then goes back to the sump. Okay. So, that is done, rotor cooling was also done by the oil coolers. Okay. And then there are, the rotor is also cooled through the flow of fuel air mixture. So, fuel air mixture comes in, cools the rotor, because rotor is also one of the hot parts. Rotor is basically just like a piston, and I told you in an engine, piston becomes most challenging to cool the piston in a reciprocating engine. Similarly, here also the rotor becomes a weakling because there is no way you can cool it. So, I think the only way you can cool it is that allow the fuel air mixture to go in and absorb some heat, and then before it enters the intake circuit. So, the air comes in, goes through the rotor, and then comes out. Okay. So, this is the total exhaust control system. So, in the exhaust control systems, just like reciprocating engine, what kind of pollutants you expect? So, obviously This is a spark ignition engine, so you do not expect particulate matter, but you expect HC, CO and NOx, all these 3 emissions you expect. So, they have to be controlled. So, there are 2 ways to actually control them. First is that you can have thermal reactor system. Thermal reactor system means whatever exhaust is coming out, you actually heat it and allow the whatever incomplete combustion reactions have remained, you complete those reactions, and finally HC and CO should be converted into carbon dioxide and water. Or you can have catalytic system. Catalytic system you can have, just like we use 3-way catalyst for spark ignition engines, which actually reduces the NOx into nitrogen and oxidizes carbon monoxide and hydrocarbons into carbon dioxide and water. So, these are the 2 types. So, this is the intake, air cleaner, this is where the air comes in, this is the air valve control, then the air goes in, pollutants are formed, and this is the thermal reactor system. And then you can have, in the thermal reactor system, since the oxidation has to happen, you have to supply secondary air. So, from here some of the air should come in as secondary air, which completes the reaction, because oxygen has to be made available if you want reactions to proceed. These are oxidation reactions, and then they go out. Okay. So, thermal reactor system, it is very compact design, you have less heat loss from the thermal reactor systems, it promotes the oxidation reactions, it prevents the heat deterioration. Catalyst system, catalyst system is, you can have some kind of a catalyst which will oxidize the carbon monoxide and hydrocarbon and will reduce the NOx. So, basically you need 2 sets of catalysts, one is oxidation catalyst, the other one is reducing catalyst. Okay. So, and this is just like monolith. Monolith means one structure made of single piece, which is honeycomb, and then you coat catalyst on it and then allow the flow of the air. It is a flow through device, that means it does not stop the flow or retard the velocity in any way. Okay. So, air gets oxidized or reduced, pollutants get oxidized or reduced on the go. But one of the important reactions, one of the important conditions for these oxidation and reduction reactions to happen is that they have to obtain a certain temperature, which is of the order of 250 degrees centigrade. So, catalyst will generally, oxidation reactions can happen at relatively lower temperature because you are using catalyst. So, and that temperature is about 250. So, you see this, this is a 3-way catalytic converter. You allow the secondary air to come in, okay, and this is a reducing catalyst, okay, and this is the oxidation catalyst. So, oxygen is coming in and oxidation takes place. So, this is how it looks like. Okay. So, in this reducing agent, you see here, this is on the rich side, this is on the lean side, NOx is formed. So, NOx is neutralized by this reducing agent. So, NOx reaction, NOx concentration comes down. This is the oxidation catalyst. So, hydrocarbon and carbon monoxide, they actually decrease, their conversion efficiency decreases. This is stoichiometric, this is the lean side. Okay. So, this NOx conversion efficiency will be very high when the mixture will be rich. Here, NOx conversion efficiency will be very low when the mixture will be lean. Why it will be lean? Because the catalyst needs to reduce, it needs oxygen. If the oxygen is already present in free form in the exhaust, why it will take, why it will engage with the NOx? Because to free the oxygen from the nitrogen, it has to provide some energy. Why will it provide when it is available free? So, NOx catalyst does not work when mixture is lean. Okay. CO and HC, they form very heavily when you do not have enough air available, you are on the richer side. Okay. So, the main catalyst is incorporated with 2 beds of efficiently purifying HCCO and NOx in the exhaust system, and there could be a pallet type of catalytic converter containing 2 bed types. One is the oxidizing type, the other one is reducing types. Now, if you look at the exhaust emission characteristics, flame quenching means the flames will get quenched when they come closer to the walls. So, you have almost the same fundamentals as that of reciprocating engine. Here also you have lot of surface area, incomplete combustion will take place, blow by of the partially burnt gases will take place, unburnt fuel. So, these will cause some important, these will cause emission problems. So, unburnt hydrocarbon, why they form? Quenching of the flame front due to contact with relatively cooler metal surfaces. Okay. Flames cannot go all the way to metal walls. Okay. And another mixture could be rich mixture or poor mixing of fuel and air. And another reason could be mixing of the lubricating oil. All the lubricating oil that you are putting in will not burn completely. And if it does not burn completely, then it will come out in the form of hydrocarbons. Okay. So, the effect, all this, all these hydrocarbons that are forming, they may form a layer of unburned or partially burned fuel near the surface. So, this is what is going to create problem. Blow-by emissions, blow-by emission from the rotary engine are not much. Blow-by, what is blow-by in a reciprocating engine? The blow-by in a reciprocating engine is that the top chamber is pressurized, rings are sealing, and the bottom chamber, which is crankcase, is unpressurized. So, some of the gases can pass through from the top chamber to bottom chamber. Here in this case, what are you sealing against? You have this chamber which is being pressurized. If it passes through the ring, where does it come? To the next chamber. So, the next chamber will burn next. So, even if there is a blow by, the charge will not come out, it will burn. What will happen is, when you are coming here, intake is there. If the blow by comes out into the exhaust, if this side, from here to here, this ring, that will go into the exhaust. So, that can create some blow by, but here the pressure will not be very high. So, it is not a major problem, but leakage past the trailing apex seal is mixed in the next chamber. The leakage past the leading apex seal is a direct loss, as it goes directly into the exhaust. So, that is the only loss that will happen. Okay. The emission characteristics of the rotary engine are affected by load and speed, just like any other engine. Hydrocarbon concentration increases as the speed is increased, but decreases with increase in load. So, when you are increasing the load, what happens in an engine? You are basically doing the thermal loading of the engine. Engine will run hotter, temperatures will be higher, and when the temperatures will be higher, what will happen to carbon monoxide and hydrocarbon? They will get destroyed, they will get consumed, they will get oxidized, they will burn more efficiently. So, this is what happens. Speed is high. When the speed is high, you are giving less amount of time. So, the time may not be enough for conversion of hydrocarbons into carbon dioxide and water. So, they will get converted to partial combustion product. That is why when you increase the speed, lesser time is available, and therefore, more hydrocarbon concentration is seen. Okay. If you increase the coolant inlet temperature, so if you increase the coolant temperature, that means you will be running the engine hotter, and if you are running the engine hotter, what will happen to hydrocarbon emission? It will reduce. Okay. So, these are some of the effects. And then combustion chamber shape, etc. These are some of the characteristics which show what is the effect of this is a engine, rotary engine with 673 cc rotor and 2 rotors, and here the vehicle is running at 40 km/h and 80 km/h. Engine is rotating at 1430 rpm and 2850 rpm, and then this is the pressure, and you can see the characteristics. So, this just shows carbon monoxide emissions, hydrocarbon emissions, and NOx emissions. I think the spirit we have already discussed in the previous class. So, let me just compare finally the reciprocating engine with the rotary engine. The rotary engine converts the expansion pressure of the burnt fuel mixture directly into the turning force of the triangular rotor and the eccentric shaft, and there is no need for any connecting rod. Whereas in a reciprocating engine, you definitely need connecting rod and crankshafts. Okay. The intake and exhaust ports are opened and closed by the rotor movement itself. In a reciprocating engine, most of the time, except 2-stroke engines, you always need camshafts, tappets, and valves, and push rods, and all those things. Okay, valve seats, all this is required. Valve mechanism, which include timing belt, camshaft, rocker arm, valve spring, etc., required in the reciprocating engine are not required in Wankel engine. So, it makes the construction extremely simple. Okay. With the reciprocating engine, piston motion itself could be a source of vibration, because piston has to change its direction, and that it causes vibrations, right, while the valve train generates unwanted mechanical losses. Smooth turning motion of the rotary engine generates considerably less vibrations, and the absence of valve actuating mechanism contributes to smoother and quieter operation. So, compared to reciprocating engines, rotary engines are much more smooth and ride will be more comfortable. When it comes to durability, the rotor turns at 1/3 of the engine speed. So, if the engine shaft is rotating at 6000 rpm, this rotor will be operating only at 2000 rpm. Therefore, when the rotary engine runs at a speed of 7000, 8000 rpm, rotor is turning at 1/3 of that rate. In addition, since the rotary engine does not have such high speed moving parts such as rocker arm, connecting rod, it is much more reliable and durable under high load conditions. Okay. Now, if we compare the torque fluctuation of the rotary engine with the reciprocating engine. So, here you have the average torque and here you have the fluctuating torque. Fluctuating torque, I showed you that graph where the torque was fluctuating all the time. So, this is the inline 4-cylinder engine where the torque was fluctuating quite a bit. So, you can see for an average torque of even 25, the fluctuation will be 115 Newton meter. Okay. This is the reciprocating engine, which is 6-cylinder engine V6 configuration. Okay. And this is the V8 configuration. So, as I said, you know, if you have V configuration, more number of cylinders, the balancing is better and the fluctuating torque comes down. So, rotary engine of 2 rotor only will have comparable fluctuating torque as that of V8 engine, V6 to V8 engine. So, it is actually much less, much more comfortable compared to reciprocating engines. So, the rotary engine has a rather flat torque curve throughout the whole speed range, and according to research results, torque fluctuations during operation are at the same level as inline 6 or 8-cylinder engine, even with 2 rotor design, and a 3 rotor design is even more smoother than the V8. Okay. So, more number of rotors you will add, obviously the comfort level will increase, the vibrations will be increasingly lesser and lesser. Okay. So, the advantages: fewer moving parts, we have seen very few moving parts. Rotary Wankel engine is much simpler, okay, and fewer moving parts, higher power output for similar displacement, higher power output it gives for every cylinder of displacement compared to reciprocating engine. One of the best things here is that you can actually use lower octane number fuels, and this is where I see a future of the Wankel engines coming back to the market. Reason being that, you know, now you have seen that most of the oil that we are producing in the world, we are not able to discover new oil, okay, and we have taken out all the possible oil that we could take out. So, we have taken out only about 1/3 of the oil from oil wells. The remaining 2/3 of the oil is what we call as heavy petroleum oil. So, it is stuck with the walls and, you know, it is heavy and not so good. So, now with increasing time, say 10 years, 20 years down the line, that has to be taken out if we have to run our engines. And when that has to be taken out, since it is poor quality, when you do the refining, the octane number of the fuel that you will generate will be going to be lower. Okay. So, you need technologies. So, you have two options. One is that either you try to increase the octane number in the refining process, which is going to be very cost intensive. Okay. The second aspect will be that you develop the engine technologies which can accept lower octane number fuels. Okay. And this is one such technology where, you know, in the Wankel engines, the fuel of lower octane number can be used without pre-ignition or knocking. Okay. So, knocking is just very little possibility of knocking in the Wankel engines, because everything is happening much faster. Okay. There is no need of any additional component such as connecting rod, conventional crankshaft balance weights, etc. So, it is a much lighter, much smaller engine which can produce same power output, and obviously it is smoother operation. Okay. So, it can even run at higher RPM without much of a problem. But there are certain disadvantages. One disadvantage is that the time available for fuel injection in the Wankel engine is significantly shorter. Okay. And then there is more complicated fuel injection technologies are required, but that is not a problem these days, because now we have introduced a lot of electronics in it. So, this part which used to be a problem now is no longer a problem in current scenario. So, in terms of fuel economy, Wankel engines are generally less efficient than 4-stroke engines because of the leakage issues. Okay. So, that is one big problem. Sealing leakage is one of the big problems, and that is one reason why now, from in spite of having a 1968 top of the best car in the world, which is rotary engine, we do not see rotary engine cars in the market now for two reasons. One is sealing is a big problem, the other one is because of the sealing losses, the efficiency is also less, mileage is also less, pollution is more. Okay. And they are low compression ratio engines. So, there is a certain amount of compression ratio is limited by the geometry, right, how much you can compress. So, there are low compression ratio engine, and since there are low compression ratio engines, obviously there is thermal efficiency. We know the Otto cycle, it depends on compression ratio, efficiency depends on compression ratio. So, thermal efficiency and fuel economy are therefore also low, and that is why they are not very popular so far for automotive application. But please remember that when it comes to UAVs, for example, if you want to have a UAV on say Naxalite area, you have to do some recce and you want a UAV, what power plant will you choose? So, there you do not worry about fuel economy that much, there you worry about whiteness, right, no noise. Okay. So, low compression ratio causes thermal efficiency issues and also the fuel economy issues. Okay. So, I will just give you two small pictures, here this is one motorcycle. So, motorcycle is having rotary Wankel engine, then you have very nice cars which used to have a Wankel engine, then race cars, obviously it makes a lot of sense to have race cars which are running on rotary engines, jet skis, go-karts, because there you have very small space, but you need a lot of power and you do not worry about economy, you do not worry about emissions in these applications. So, and then chainsaws, if you want to cut down trees, this is used as APU. So, this is Norton two-rotor Wankel motorcycle, Wankel engine is located here, and this is the Mazda RX-8. Okay. So, this is all that I wanted to talk to you about Wankel engines. Thank you very much.